Hello, in this video we are going to learn something very fundamental to astrology, which is how do we know where the planets are in the sky? How are their positions calculated? Because obviously in astrology we're interpreting the positions of the planets. How do we know where they are? Well, the way we know where they are as astrologers is we run our computer software, or we look in an ephemeris, which is a book or an online set of tables that show you where the planet positions are, and there is an ephemeris feature in the Sirius software where you can look them up. But my question is not how we do it as astrologers. How do we know where they are in order to put them in the software or to put them in an ephemeris? So as astrologers, we often think of calculating a chart manually as looking in an ephemeris, but that's really not getting to the heart of it. An ephemeris is just a list of planetary positions. How the heck did those positions get in the book? And that's what I'm going to describe in this series of videos, because this will take more than one video to explain this. So what we're saying is, let's determine where Mercury is, or Venus, or any other planet at a certain date and time. How is that done? And there is another benefit to this, in addition to just the satisfaction of understanding it, to kind of wipe away that mystery a little bit. There's also some practical implications when you understand how planetary positions are calculated. For example, you will understand what the moon's mean node really is. And very, very few astrologers know what it is astronomically, as a thing. What actually is it? And what actually is the true node? And is the true node really true? In other words, is the true node where the moon's node really is? And some astronomers, who are also astrologers, say that the true node is not necessarily where the moon's node really is, but we've done some additional investigations, calculations, and analysis, and we've determined that the true node really is where the moon's node is. It really is true. And we're going to learn about that as well. So that's one of the practical benefits of learning this. Also, just curiosity, like, how the heck do we know this stuff? Okay, and again, and to mention this in a little more detail, some astrologers state that if you know how to calculate a chart without a computer, so you're not dependent on a computer, you can go to a book called an ephemeris that lists the planetary positions once a day, and something called a table of houses to find out where the house cusps are, and you're able to do these calculations based on the birth time to figure out the planetary positions. If you learn how to do that, and I think most people do not learn that now because it's not required, some astrologers say, well, it's very important to learn that because it tells you what's underneath just the chart wheel that you're looking at using your computer software. Personally, I do not really agree with that very much, because by learning how to use an ephemeris and a table of houses, all you've really done is look through a bunch of tables. The real question to me is, how the heck do astronomers know what the positions are at all to stick them in the table of houses? In the ephemeris. How are they actually calculated? Not just printed in a book, their daily positions. So learning how the planets are actually calculated really gives you some insight into the underlying astronomy. And like I say, there's some practical implications of that. So again, if you've learned how to use an ephemeris, or if you've been told that you really need to learn this so you really understand how planets are calculated, just to underscore this point, you really have not learned anything. You've learned nothing about how planetary positions are determined, how they're actually calculated. So wipe that idea out of your mind because it will just confuse you. Again, an ephemeris is just a list of the positions once a day. Those positions are not known through observation. They're calculated using formulas, and they're confirmed by observation. You can go and look, and you'll see that they're accurate. But the way they get into the book is through a formula. I'm going to show you what the essence of that formula is, what the basic concepts behind the formulas are. Now, what is the formula for calculating where a planet is? So here we have an image of the sun and the Earth going around the sun. So you know the Earth travels around the sun, and all the planets do: Mercury, Venus, Earth, Mars, Jupiter, etc. Excuse me. They travel around the sun in this kind of egg shape we call an ellipse. And some planets have a thinner ellipse, and some it's closer to being circular. And how skinny the ellipse is, or how close to being perfectly round it is called the eccentricity, which literally means off-center or off-circular. How far from perfectly circular it is. And there's a measurement given to, and in this case it's 0.6, but right now, don't worry about where that 0.6 value comes from. All we want to know is that the planets travel around the sun in this ellipse, which is like a flattened circle, and for some planets it's flattened, made skinnier, and for other planets it's closer to round. Every planet going around every star, and every satellite, the moon going around the Earth, everything travels in an ellipse. And so far that's been confirmed by astronomical observations. No exceptions to the rule have been found yet. Maybe one day an exception to the rule will be found. But so far everything that's been found travels in an ellipse. So that's rule number one for calculating where the planets are. Rule number two is this. As you look at this image in the lower right corner of the sun and the Earth going around the sun, as the Earth moves once a year, revolves around the sun, and it revolves counterclockwise if you're up at the North Pole, if you're above the North Pole looking down, you would see the Earth going counterclockwise. If you were at the South Pole looking up, it would be the reverse. It would be clockwise. So imagine you're looking down, you're up in the sky somewhere, looking down on the sun and the Earth. Over time, you'll see the Earth move around the sun, following this elliptical path. And when the Earth is closer to the sun, it's faster. That's one of the big breakthroughs that Kepler made. Number one, he came up with the idea that planets are traveling in an ellipse. Number two, he came up with the idea that the planet is speeding up as it gets closer to the sun. And he makes this guess, and then he compares it to where planets actually are, and the guess is correct. He comes up with a formula for how much faster the Earth is going as it gets closer to the sun and how much it slows down. He comes up with a formula. We're going to learn this one step at a time, but this is the understanding. This is how astronomers calculate where the planets are and can create an ephemeris or software that creates your astrology charts and everything that we do as astrologers, or everything that astronomers do. They apply these formulas based on this understanding. Now, just as an incidental kind of note, for a while Kepler was working for this fellow Tycho Brahe, and Tycho Brahe had an observatory, and he made extremely careful measurements of where the planets are and he recorded them. He just made a list of where they are. And he did it more precisely than probably anybody else or nearly anybody else had ever done. And there were already formulas for predicting where the planets are. These are formulas that Placidus used and have been handed down since then. And those formulas that were used worked fairly well, but not perfectly. So you would run it through these formulas that they had, and it came out, fairly close, I think within about a half a degree or something, typically. And Brahe wanted to improve the formula, get it more precise. And in order to do that, he had to have precise positions of the planets. So he recorded those. And he gave to Kepler just Mars. He had recorded, all different planets. But he said, here's Mars, here's the positions. Can you improve on the formulas we have to match where Mars is? Kepler called this his war with Mars. And Kepler was also an astrologer, and clearly he understood the double meaning there, the double entendre, that Mars is the planet of war, and his war with Mars to try to figure out a formula to match Mars, and he figures it out. Step number one, he decides the sun is the center of the solar system. Well, he doesn't decide it. He agrees with Copernicus and other people who had that theory that the sun is the center. The Earth and the other planets are going around. Mars is going around the sun. And it was firmly believed that the orbits were circular. One of the reasons they thought the orbits were circular is that they thought the manifest world created by God had God's perfection in it, and the circle is perfect. So they had this intuitive feeling that the planets must be traveling in circles. Well, when he changed it from a circle to an ellipse, and then he started adjusting the speed by going faster as the planet gets near the sun, this provided a foundation for figuring out exactly where the planets are. This is a long, tedious, tricky process to figure out a formula that predicts where planets are, and Kepler achieved it. Now, let's watch this video, about just 15 seconds of a YouTube video that shows a planet speeding up and slowing down, speeding up as it gets closer to the sun and slowing down as it gets farther away. So again, we have an image of the Earth here on the right side, and there's the sun. Notice that the planet, again, is traveling in an ellipse, and the sun is not at the center. It's not directly in the center. It's off to the side. That's the way an ellipse works. So the sun is off to the side a little bit. And Kepler's rule is that the planet speeds up as it gets closer to the sun. And I'm going to play this animation that shows it more carefully. We'll talk about this a little bit later in more detail, but I'll give you a preview to it. It's up here at the top of this, YouTube video. This is the second law of Kepler. Remember, he has three laws. His second law is that a planet sweeps out equal areas over equal time intervals. So you see on the right side, the Earth would travel this gray slice. This looks like a slice of cake or a slice of pizza. The area of this slice, let's call it a slice of pizza, is the same as the area of the one on the left side. So the Earth, or any planet, and you're showing an image of the Earth here, but any planet with this elliptical shape will travel from the beginning of this gray area to the end of it in the same time that it will travel this much bigger arc on the left side. So if you're giving two people an equally sized slice of pizza, the actual pizza is the same. The one on the right and the one on the left are the same size. The one on the right is long and skinny. The one on the left is, shorter and look more squarish looking, but they're the same exact size. And somehow he comes up with this idea that the planet will sweep out equal areas in the same time. And that shows exactly how much faster the planet is moving as it gets closer to the sun. This mathematical formula, that he comes up with, it just works. It just works. It ends up being true. It's kind of amazing that he would ever think of this. Like, how the heck would you think of planets sweeping out the same area in the same time? But somehow he comes up with it. And how does he know he's right? Because he's got the position of Mars every day, and he makes this elliptical shape for it, and it works. So by this kind of lucky breakthrough of stumbling on this formula, he sets a foundation for being able to predict the positions of planets more accurately. Now I'm going to play this animation, and it's just going to show the Earth speeding up as it gets closer to the sun. So ready, set, go.
The distances traveled by the planet, either C to D or M to N, in order to sweep out these areas are of different magnitude.
Okay, he's going to start moving it.
However,
there it
the
goes.
planet moves faster when close and slower when far away, in a manner that results in precisely equivalent time intervals. And Kepler's third law...
Okay, so you see how the Earth speeds up as it's on the left side. I'm going to play that again. Make sure that you see this. And
areas are of
different
magnitude.
He's talking. I don't know if you can hear him. There, the Earth is going slowly,
when close, and
speeding up,
far away, in a manner that results
and then slowing down. Okay, so this is how planetary positions are calculated, by understanding how the planets move. They travel in ellipses, and they speed up according to a very specific calculation of sweeping out equal areas in equal times. Once you know the math to figure out those areas, it all works. And that video, by the way, gives more details about the Kepler's laws of motion. You can watch that video if you want. We will be covering those ideas as well in this series of videos. Okay, so what is important to us is that Kepler's laws of motion tell us where a planet is, period, full stop. That's my point. It's Kepler's laws of motion are used to produce an ephemeris. The ephemeris is created from these formulas. An ephemeris is not created by somebody having observed where the planets are every day and guess where they might be in the future. It's created from the formulas, and the formulas every time match where the planets actually are. As we're going to learn, there's, you might say, two phases to the calculation. Phase number one is to apply Kepler's laws of motion to the planet. And then later we'll learn what phase two is in the calculations, and that's when we get into the mean node versus true node and everything. Now, a little more detail about how this works. To calculate where a planet is, you need to know 6 things about the planet, about the way that that planet travels. If you know those 6 things, you can apply Kepler's laws of motion and get the position. Got it? That's all there is to it. Let me say it again. We need to know 6 things about the way that that planet is traveling in the sky. Once we have those 6 pieces of information, we can apply these formulas, and it will tell us at any moment in time where the planet is. Not extremely accurately, pretty accurately, typically within a degree or so. Fairly close. There's a second part of this to sharpen those calculations and get them even better. But you cannot do that second part without doing the first part. The first part is just apply Kepler's laws of motion to these 6 things. And what are the 6 things? I've got them listed here. We're going to go through them one at a time. What we need to know, number one, is the length of the semi-major axis. And they often use this A, small letter A, as a symbol for it, as an abbreviation. This really just means how far away the planet is from the sun. I'm going to talk about this as our sun. This is true for any star anywhere in the sky. It's true for any planet, and the moon's going around. It's true for everything. So when I say how far away that planet is from the sun, I could also say how far the moon is from the earth, or how far any moon is from any object, or any planet from any star that it's going around. This is universal. It applies to everything. So when I say distance of a planet from the sun, just realize this applies to the moon and everything else that's orbiting around something. Now, we need to know how far away the planet is. Well, we noticed, if we go back up, that the planet travels in an ellipse. So we could talk about the distance the Earth is from the sun as the maybe this long distance, or the short distance, or maybe we take it from the center and take half that. We need to just come up with an agreement, a standard way of talking about it. It really doesn't matter whether we do the short distance or the long distance. Those would be two obvious choices. But, to make it convenient for everybody, we'll just have a standardized, agreed way that we talk about the distance from a planet. And the agreement is this. The distance will be the semi-major axis. Semi-major axis just means we go to the center of the ellipse. There is a center to the ellipse, a perfect center. That's not where the sun is, right? Sun is off to one side or the other. But there is a center. From that center of the ellipse, we'll measure the long way, which has an A here. And that is the semi meaning half, of the major, the larger, axis. Axis just means that line going down the middle of this ellipse. So it's very straightforward language. So what astronomers use is the length of the semi-major axis. It can be measured in meters and miles and kilometers. Some measurement of actually how far away the object is. We need to know how far away it is. So we cannot predict the positions of planets without some basic information. We have to watch that planet travel around the sun to see what its orbit is. So before we can apply the formulas, we have to make a lot of observations. We have to observe its orbit, and then just observe how skinny or close to round that orbit is, and how far away the planet is when it reaches its farthest distances from the object, how far away it is. So before you can predict where the planet is, you need to make some observations. You just have to look and see. So first we need to know what the semi-major axis is. Again, that distance is used just as a standard, just so we all use the same thing and we don't have to explain, our assumptions. It makes it simple. We'll use the semi-major axis. The second thing we need to know is the eccentricity. Okay, so there's the semi-major axis. We need to observe that, and we need to see how round the orbit is. And that's called, again, its eccentricity. If the orbit is perfectly round, like we see on the left side, we call the eccentricity 0. So that would be a perfectly round orbit. In the middle, we see a elliptical shape, and you see that the eccentricity value gets bigger the more elliptical, the skinnier and longer that ellipse is. And of course, there's a mathematical formula that determines what that value is. What we want to learn first is the concepts. somebody else can apply the formulas, but before you learn the formulas, you need to have an intuitive understanding of what this is all about. And as astrologers, I think it's good for us to have an intuitive, fundamental understanding of how planetary positions are determined. They're determined, number one, see how far away the planet is from the sun. Number two, see what the eccentricity is, usually abbreviated E for eccentricity. What is the eccentricity? These first two things you can just look up in the sky, follow that object as it goes around the sun for however long it takes it, and just observe. And then when it goes around again, you should see the same path. It does not change very much from one time to another. Over huge amounts of time, this all can change. There can be changes, but it's very, very slowly changing. Very slow. Just the way it is. Okay, so here, this is interesting. This is an image of the actual eccentricity. This is an image in the autumn of 1996. I got this from a website. I give the website address down here in a small type. I just took this from this website page where the astronomer shows the actual orbits up to Mars, just through Mars, Mercury, Venus, Earth, and Mars. And on the right side, I colored it in, because when I colored it in, it becomes clearer what's going on. And notice that Mercury has a high eccentricity of 0.21. The sun is way over to the upper right, it looks like. See what I'm saying? This purplish, pale purplish color circle, and there's the sun, the yellow. If it was in the center, it would be closer to where this U or R in Mercury is. It's off. Venus has a closer to a round orbit, 0.01 eccentricity, very close to zero. So the sun is almost exactly in the center, with Venus almost perfectly round. Earth, slightly eccentric, 0.02, still almost round. Mars has a highly eccentric orbit. So we see that the Earth is off. And they're all tilted in different directions. Notice that the large pink part of Mars is to the left. The large purple part to Mercury is in like the lower left. See what I'm saying? That if you look at that purple in the center, showing the orbit of Mercury, the larger part of this inner purple is to the lower left. The sun is closer to the upper right. For Mars, the whiter part looks like it's to the left. So they're not all facing in the ellipse, the egg shape. Let's go back to this egg shape. This ellipse on the right, the semi-major axis is horizontal. The ellipse is horizontal. If this planet is horizontal, would the other planets also have their egg shape, their ellipse horizontal? The answer is no. So the planets do not all face in the same direction. Their orbits are not stretched in the same direction. They're just whatever direction they happen to be in. Okay, so what we need to calculate the positions of the planets, we need to know how far away the planet is. That's the semi-major axis. We need to know what the eccentricity is. How close to round is the orbit? Or not close to round, long and skinny. That's the eccentricity. And the third thing we need to know, not necessarily in this order, is the inclination. Let's pick up with inclination in the next video in this series. We're getting a lot of information, so let's take a break here. You might want to review these ideas, or just, let them settle for a little bit about what we're talking about. And just to review, we're talking about how we know where the planets are. We know where they are by making 6 observations. We observe how far away the planet is, measured by its semi-major axis. We determine how close to round it is, or how skinny and long the ellipse is, and that measurement is called its eccentricity. And the next measurement is the inclination. We'll pick up with inclination in the next video in this series. Thank you very much, my friends. God bless. Namaste. And